But I want to give a disclaimer. This lecture I'm giving today, I don't have any notes on. This is completely improvised. So it went really well yesterday. So we actually are all synced up. Both classes are synced up. And I wanted to, and because of that, I also skipped some topics. We're not going to talk about like Henry's Law and Raoult's Law and colligative properties and all that junk, because I find it boring. And I'd rather spend a lot of time on equilibrium and kinetics for the rest of the semester.
Sounds good to me.
So I will post lecture notes on equilibrium, and in fact we'll go through kind of traditional chemical equilibrium concepts starting next week. But today I want to give you a different approach to chemical equilibrium. And I want to give it from what I would call a physical chemistry perspective. We're going to look at chemical equilibrium not from the idea of doing an ice chart, right? Where you have moles of stuff and you have a reaction and you add some moles of something and you see how the other things equilibrate to it. We're not going to do that yet. Instead, I want to talk about what equilibrium is and how, and actually it's a really simple concept and the physical the underlying physical principles of chemical equilibrium. And come up with a really nice way to talk about how to measure a equilibrium without measuring concentrations or anything like that. We're going to just have a box of molecules that may react and form other molecules, and we're curious about the ratio of the products and the reactants. So we'll do it without even defining volume or concentration. We're just going to have numbers of molecules. We'll have N reactants and N products. They'll have an energy difference between them. And that's all we need to know about them to calculate chemical equilibrium. So bear with me. It went pretty well. And unfortunately, I should have written notes down because now I don't remember everything I talked about, so we'll do my best. What I want to start with is, again, kind of a motivational example of a reaction. And the reactions we're going to look at are very simple ones today. The idea that you have a single molecule, A, and it's in equilibrium with something else, B. Maybe there's some other products, but we'll just keep it really simple. Not a bimolecular reaction, just something unimolecular. A converts into B. And I'm going to use kind of as a motivating example a reaction that I studied in when I was at Argonne a couple years ago. And it's the decomposition of acrylonitrile, which is this molecule. It's a double bond. It's just an ethylene with a CN group on it. Right? Acrylonitrile. We often call this, so the name that Aldrich gives us is acrylonitrile, but most chemists call it vinyl cyanide. And that's it's actually a stable molecule. You can buy it. It comes in a liquid. It's a really nasty molecule. But under UV light, it decomposes spontaneously. So if you shine a UV light at it, let me get a better black marker. If you shine a UV light at it, for instance, a laser, right? I'll often write light as h nu, which is the energy of a photon. We haven't gotten there yet, but maybe you've seen h nu before. For light, this means light. For instance, the wavelength we typically use for this is 193 nanometers, which is in the ultraviolet, UV light. This molecule will fall apart. All right, and I'll just kind of talk very briefly about how it falls apart. It falls apart in many different ways, but I want to focus on a particular result, the most common result, which is that you end up getting acetylene and HCN, hydrogen cyanide gas. Okay, and there turns out to be two ways to do it. There's two mechanisms and they compete. And so the first mechanism, just to show you, just out of curiosity, just for interest, this isn't really relevant to our discussion, but it's interesting, I think. The first mechanism, let me draw it out. The first mechanism is what's called a four-body dissociation, where this hydrogen attacks the CN, and the electrons kick that hydrogen out like that. It's four-body because there's 1, 2, 3, 4. Kind of makes a square, if you will. So the intermediate or the transition state for this looks like this. This is the transition state, and then you get acetylene out. I'll make a fake double, triple bond there. An HCN. All right, so that's one mechanism. And in fact, that's the dominant mechanism, but there's another one. Where you get what's called a three-body dissociation. I'll draw it out. Where this hydrogen attacks the CN instead of across the bond, it's the one that's vicinal to it. So the transition state for this looks like two hydrogens on this side, and then a hydrogen dissociated on this side, form HCN. Now notice when HCN leaves, you're left with non-acetylene because the hydrogens are on the opposite, they're on the same side, they're not on opposite sides, so it's not acetylene. What you form is what's called vinylidene, which is a carbene. It's got a lone pair here on this bond. And vinylidene isomerizes to acetylene extremely quickly. If there's enough energy in it, this hydrogen just moves over here, and you get the same products again. Okay, so there's two different mechanisms for that, and they compete. And in fact, some of my research I was doing was looking at the competition between these and trying to figure out if you can see kinetics or reaction at forming these as well as these. They have different signatures energetically because they form differently, right? So we're looking for signatures or fingerprints that you can distinguish between molecules that form through this pathway versus this pathway. All right, and I won't talk about that here. We'll come back to this when we talk about kinetics where it becomes more relevant. But the idea is that the question that I want to ask now is, after this happens, right, we let the system equilibrate and everything is normal, how many products are formed relative to the starting products, right? Do all the starting products go away? Is there a balance between them, right? Is the yield 100%? Is it not 100% at equilibrium? Right? This is a classic equilibrium question. Okay, and so the way that I want to look at this is I want to make a plot. All right, and we're gonna think about the Gibbs energy of this reaction as we go through it. So delta G on the y-axis, and then on the x-axis I want to plot some trajectory. Right, this if you think about it, these atoms, they're moving around. And they're flowing, they're moving in space in a certain way, right? You form a bond here, and then the HCN leaves, right? And imagine that we can take all those coordinates and we can express them on a single path, right? We measure the energy of the system as it moves through a mechanism, all right? And it turns out that you can specify a one-dimensional path, even though there are many things moving, right? You're adjusting multiple bond lengths and angles. You have these products moving away. There's lots of different coordinates in your system of things moving in time. But you can show that because energy is a state function, we only need to worry about the initial point and the final point, and then we can find a path of least resistance, if you will, from the beginning to the end. Right? And so what you find is that delta G is negative in this reaction, so your products are like right here, or your reactants are here. This is our reactant energy. So this is vinyl cyanide, H2CC, HCN. And this coordinate we call as a reaction coordinate, right? It's just a generalized trajectory for all the atoms moving from products to reactants to products, okay? It doesn't really have any geometric meaning. It's just a combination of different things moving together, and we represent it in one dimension or two dimensions. We'll talk more about reaction coordinates when we get to kinetics, where they become very important. But just bear with me. And so if you model this reaction and you model Gibbs energy as you move through this path of least resistance from the reactants to products, you find that the energy increases until you hit what you call the transition state, which is a hump. And then there's a big downhill reaction, downhill exothermic reaction to the products. Okay, so there's a big barrier. In fact, the barrier is so large that at room temperature, acrylonitrile can't decompose very fast because the barrier is much higher than the thermal energy at 300 Kelvin. So that's why we use a laser to do it, because the laser pumps you up really high in energy. But bear with me. All right, so we can immediately know what the delta G of this reaction is. All right, here's the G of the starting products. Here's the G of the final products. So delta G is just the energy difference between these 2 points. Okay. But we have to also make a consideration that, or what we call detailed balance, or microscopic reversibility, the principle of microscopic reversibility, which basically means that for any microscopic process or any reaction, there is a non-zero probability of products to re-react and go backwards to form reactants. Right, so we can break apart vinyl cyanide to form acetylene and HCN, but if these two molecules go back and collide together, they also have an ability to just go right back. Right, so we have to consider the fact that sometimes you're going to have forward reactions, sometimes you're going to have reverse reactions, and the question is which one's more likely? Right, that's actually the point of equilibrium. The point of equilibrium is that a system, let me be more careful, equilibrium is reached when a couple things happen. One is that all components of our mixture, so the reactants and the products, can be expressed with a single temperature. T. All right, so that's being thermal equilibrium, right? The whole point of thermal equilibrium is that the entire system's at one temperature. And two, that the rate of formation of products or reactants approaches zero at infinite time. So what I mean by that is if we were to monitor the products as a function of time, so we'll say the concentration of HCN, for instance, or the number of HCN molecules. At initial time, there are none, right, because we only have vinyl cyanide. And then as they start to react, you start forming HCN, and then eventually it'll start to level off. Right? This means that the change in HCN with respect to time is zero, right, which we call steady state. Right, so the equilibrium is reached when everything's at the same temperature, and that we've reached steady state. That the molecules are the concentrations of the products and the reactants aren't changing anymore. They've come to some equilibrated value. All right, and we don't know what that value is yet, but we will in a minute. But the idea is that we have to wait long enough for the system to reach steady state, right? That there's a thermodynamic balance between the reactants and the products, and that everything's at the same temperature and everything's kind of reached equilibrium, if you will. Right. So in general, equilibrium is typically only reached as T goes to infinity. Right? We don't know how fast this reaction occurs. It may occur really quickly. It may occur over the course of 10 million years. We don't know. But equilibrium isn't going to be reached until these things are satisfied. And so kinetics will answer the question, how long is it going to take? But we have to know that the system, if the fact of the matter is that everything can be expressed at the same temperature, it all equilibrates, then that means everything's reached steady state anyway. These are actually basically saying the same thing. Okay? So, but we have to consider them both independently. So again, equilibrium is going to be really useful because what it's going to tell us is, well, how many products actually form. Right? It's going to tell us the distribution of products and reactants. But it's not going to tell us how fast things happen. Right? We don't even know if this reaction happens at all. Because if we look at this, right, delta G is less than 0 in this case. We know that this reaction is spontaneous and product favor. But we don't know if those products are ever going to form. Right? Kinetics will answer that question for us. So equilibrium is an assumption that at infinite time everything's equilibrated and the system has a chance to sample the products and the reactants. Okay? It's got a chance to be everywhere. The system samples all possible configurations. Right? And that might take forever. We don't know. But we just make that assumption. Right? What happens if we wait, if we have a reaction that we care about? What do we measure if we waited infinite amount of time? So sometimes equilibrium is never reached, but we can make an assumption that it is. Okay. So now the question is this. So the big question I have is this. What is the ratio of products over reactants? Okay. So I'm going to do it in a very simple way. I'm going to ask the question now, what is the product of the number of the ratio of the number of product of molecules, the number of molecules, right, over the number of reactants? Okay, and we need to calculate this. We can calculate this using just a couple of assumptions about this graph right here. So what are those assumptions? First, we're going to make it easy. We're going to assume the system has reached equilibrium. So set temperature to T, whatever T is, and that all components are ideal gases. All right. Now we have to use what we want to use about ideal gases. Of course, we can use Pivner. That'll be useful for us in a minute once we get to an expression. But we want to use ideal gases because ideal gases have a random statistical distribution of energies. Right? We said that the whole point of ideal gases, they move randomly. Right? They have a random amount of motion. They're distributed with a probability distribution of energies, and then so everything's just random and statistical. Right? This is just saying everything is random. Everything is sampled randomly. And is statistical. Take care. Okay, and so we can come up with a really simple equation. We can write the number of a certain molecule or state over the total number is proportional to the energy of this molecule of that state over kT, RT. All right, Boltzmann distribution. So what that means is, the energy of the molecule. The energy of the molecule over RT. Okay, and so let's look at it here. End products over end reactants is the same as writing the number of products over the total number of molecules over end reactants over number of total molecules, which is going to be the energy of the products, E product, over RT, or KT. We should use KT here, but that's okay, we'll change it later. Divided by E to the minus energy of the reactants over RT. And when you do this math, what you get is that this difference, the end product over end reactant, is E to the minus difference between the product energies minus the reactant energies over RT. Now, what's the difference between the product and the reactant energies? Well, it's just delta G, right? Here's our product energies. Here's our reactant energies. Sorry, other way. Here's our reactant energies here. Here's our product energies. Here's our reactant energies. The difference is delta G. All right, so this is going to be E to the minus delta G over RT. Now, I'm going to show you this graphically. Now, what this is assuming, though, is that the energy of our molecules are at this point right here. But in fact, they're not, because they're ideal gases. Ideal gases always have a fixed amount of energy. As they have the average thermal energy of them, the average kinetic energy, if you will, is 3/2 RT. So what I'm going to do now is draw 3/2 RT on this scale. So if we let this be energy 0, and let's let this to be 3/2 RT, our molecules are not actually at this energy, but in fact they're at this energy. Right? And likewise here. We'll take this difference, put it here. So these molecules are at 3/2 RT here. The products are at this energy. Right, they have some thermal energy because they're ideal gases. They have kinetic energy. So what that means is that we need to account for the fact that there's a little bit of thermal energy in these molecules. So in fact, E product will be 0 plus 3/2 RT, and whatever this value is, 3 plus 3/2 RT. But those 3/2 RT cancel out, right? So it doesn't matter. You have 3/2 RT here and 3/2 RT here, and you're taking the difference, and so it goes away. So it's still only dependent on delta G. However, if we look at this, if we instead look at, I'm going to draw an extra plot right here, vertically. If we ask what is the fraction of molecules at a given energy, of course, the mean energy of them is at the thermal energy right here, and there will be a distribution that looks like this, like that. Right, so the reactant molecules are distributed in terms of energy in this region right here, and we can draw the same thing for the product molecules, like this. Okay, so this is just the distribution of energies. So the mean of the energy of all the molecules, reactant molecules, is here. There's some distribution. And here there's a distribution of product molecules in the same way. All right, so 3/2 RT is their mean energy. Right, so in order for a molecule of, I want to make this a little more dramatic actually. Like that instead. Let it kind of decay off slowly like that. So there's a little bit of decrease. in order for imagine now a molecule, this is a classical object, imagine it's just a sphere, all right? And you want to roll that sphere over this hill, right? So in order for a reactant molecule to get over this barrier and to get to the other side, is that needs to have enough energy to crest the hill, right? So if I pump the ball up or the molecule up to this amount of energy, what's going to happen? Well, it's just going to roll right back down, right? It's not going to react. Right, so the only molecules that can come over are the ones that have enough energy to cross the barrier, right? Which is right here. Right, so only the molecules here in the shaded region these molecules react to form products. So with this drawing, not a lot of molecules get over, but some do. Okay, and so let's look at it from the other perspective. Well, for backwards, right? So backwards, what molecules can cross over into here? Well, it's only the ones with sufficient energy. So the only ones that can cross for the products to go back to reactants are the ones right here. In this region. So I'll just draw it like this. That. Right? So we could say that maybe this is 20% of the molecules, but this is only 1% of the molecules, right? So right, we know that this, because delta G is less than 0, is product favored, right? That you're going to form more products than reactants in the end. That's what this says, that this is spontaneous. But what it means statistically is that there are more reactant molecules of a sufficient amount of energy to get over the barrier than there are product molecules to go backwards. Right? And so the difference between this number of molecules and this number of molecules is just e to the delta G over RT. Right? Because ultimately it's set by this distance, right? So this is much lower in energy, so thermal energy only adds a little bit of energy compared to the barrier on the product side, but on the reactant side, the barrier is much closer to the reactant, so the heat of the material allows you to get molecules over more easily. Right? And the ratio of these reactive molecules, reactive reactants versus reactive products, is still just e to the minus delta G over RT. We're going to come back to this when we go to kinetics. We'll look at this exact same schematic, and with this knowledge, we can also calculate the rate constant for this as well. But we're not quite there yet. So what that says is that the number of product molecules over the number of reactant molecules is equal to e to the minus delta G over RT. And now what we want to do is, it's kind of hard to measure this, so we should instead measure, it's kind of hard to measure the number of molecules, so instead we should convert it to something more reasonable. So what we can use is the ideal gas law, which says that the number of moles equals PV over RT. And what is the number of moles? The number of moles is the number of molecules times Avogadro's number equals PV over RT. So we have molecules times per mole. Oh, sorry, I have this wrong. It's per mole. So, and the number of moles is the number of particles, or number of molecules divided by n sub a. All right, so that's particles. This is particles per mole, so overall it's moles. Which means that n particles is equal to PV over RT times NA. Avogadro's number, but R is equal to Boltzmann's constant, K sub B times Na. So N, the number of particles, is PV over KBT. Okay? So now we can plug that into our expression for the ratio of products. So let me bring it back over here, or I have it already. Use a different color here. So this end product is going to be the pressure of the products, the partial pressure, times the volume of our container, times KBT, over the pressure of the reactants, times V. Of course, V is the same in both cases. They both exist in the same box, over KBT. All right, and everything cancels out. Right, the volumes cancel out, the KTs cancel out, and what you're left with is the pressure of the products, the partial pressure of the products, divided by the pressure of the reactants, is equal to the negative difference of G, e to the minus delta G over RT. So if I have a gas, if this is a gas sample, if I can measure delta G, for instance, I know how many products I form, how many reactants I form. Right? For ideal gases, the total pressure is going to be the mole fraction of the products times the partial pressure, or the total pressure, plus the mole fraction of the reactants times the total pressure, which is just the partial pressures. All right, so if I can measure the partial pressure of our vinyl cyanide and the partial pressure of our reactants, well, then I can calculate delta G, or vice versa. So this equation, the idea of having the pressure of the products divided by the pressure of the reactants, we call the equilibrium constant for partial pressures, Kp. So this is the pressure-based gas phase equilibrium constant. So we have now Kp is equal to minus delta G over RT. If we take the log of both sides and multiply by RT, we have RT ln Kp is equal to delta G. This is what's called the Van 't Hoff equation. Right? And we've literally done everything we've done all of chemical equilibrium just using one graph. Right? Of course, this is only for gases. Now, we're going to have to change things when we do liquids, because liquids, you have concentrations, and of course, as we know, liquids don't mix evenly, right? They don't always mix ideally. Right? So there will be some complications in liquids, which we'll talk about, in electrolytic solutions, right, when we do electrochemistry. But we don't have to do any of that, right? We don't have to worry about any of that crap. We don't have to do ice charts to understand equilibrium. All equilibrium is just if you let your system go forever and everything stops moving and everything equilibrates, the equilibrium constant just tells you the relative ratio of your reactants and your products, right? And that's only determined by the energy difference between them, delta G. Questions about this so far? So when I talk about when I'm in physical chemistry doing gas phase science, I don't do ice charts. I don't do any of that. I just say I have a molecule that's going to react. I assume thermal equilibrium, and if I can measure delta G, which means can I measure enthalpy and entropy for my species, I know what's going to happen in my reaction. I know if it's product favored. I know if it's reactant favored. I missed a sign here, didn't I? Yeah, negative RT. Sorry, thank you. Negative RT link KP. Thank you. So we need to think about, though, that there's also in delta G, well, let's just split this out a little bit, RT ln K is equal to minus H minus T delta S. And so the question is that using this perspective of gas phase molecules, right, what's the entropy change here? Right? And there's an enthalpy change. We have a balance between the two. Right? And what we're going to find is that this difference right here, that this contribution for most gas phase reactions is actually delta H, is the enthalpy change, right? We release heat as we come down, but doesn't actually tell us anything about the entropy, right? And the question is where does the entropy come from this perspective? Right? I can replace delta G with delta H here, and everything works just fine, but how does delta H play into the role? Or delta S, right? Where does entropy come into play in this case? And there's something that we haven't learned yet, and we'll really talk about it next semester in quantum. But the important thing is that in molecules do not have a continuous distribution of energies. They can't exist at any energy you want. Let me tell you what I mean by that. I'm going to redraw this graph again. I'm going to draw it a little differently. So here's our vinyl cyanide. And here's our acetylene plus HCN. And again, our graph is in energy on the e-axis. What we'll find very quickly in next semester is that molecules experience a discrete distribution of energies. They can only be at specific energies. Right? So instead of drawing this distribution where we have molecules that can be at any energy, they can only be at very discrete levels. Right? So we'll often draw it like this, where there will be energy levels. Right? Maybe down here they have energy levels look like this. Who knows? All right, so the molecules can only exist in there. The entropy of a material is proportional to the number of possible remember, entropy is proportional to ln W, which is the number of arrangements, which is also proportional to the number of available states. Let me show you what I mean. Let me draw these same distributions, energy distributions at room temperature. Let me draw this a little more. Start to get closer. So let me draw in red our energy distribution here. Yeah. All right, so the molecule on average has energy in this region. Right, and so the question is we could calculate the entropy of it by counting the number of accessible states in this region, right? So most of the molecules are kind of in this region right here. Right, and we can count the number. Right? I don't know how many it is, but let's just say it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Right, there are 13 states in this region. Right, the entropy is proportional to that number. And we can do the same thing here. from here, like that. And there's maybe 50, who knows? Right, so what we've done is we've gone from, first of all, we've released enthalpy, right? The enthalpy, we've released energy as enthalpy by going from here down to here, right? This is delta H less than 0. Right? The system's released energy. But we've also gone from a state that is ordered, has a small number of places for configurations of Euler states, to one that's much larger. Right? Entropy is proportional to the number of these available states. So going from 13 to 50 means that delta S is greater than 0. Right? You can also think of this as we've gone from a liquid or single molecule of gas to 2 molecules of gas. Right? We've gone from an ordered system to a more disordered system. So in that regard, delta S is also greater than 0. But you may have a situation, though, imagine that you have a situation where this is flipped, where your reactants have a very high entropy and your products have a very low entropy, which just means that, for instance, the count is 13 here and 50 here. Entropy will change, but enthalpy is also the same. Right, so you have to consider the balance of those two things to determine what delta G is. And I have a really, really nice little simulation. Let me just turn, I'll leave the screen up for a second. I'll turn the camera on while we wait. I have a nice little simulation where we can take this information. We can look at the difference between the energies of the molecules, right, the bottom of these wells, delta H here, and also measure the spacing or the number of states within a certain region to get entropy. And from those two pieces of information, we can calculate the equilibrium constant. Okay. I'm going to close the screen down for a second. We'll come back to it. Okay, so what I have here on the screen is this energy level diagram. Right? Here are our reactants and here are our products. Okay, we can set the temperature. We can set the energy difference, right? You can see that the reactants are slightly lower than the products, or sorry, the products are slightly lower than the reactants, right? This is here and this is here. There's a slight energy difference. And there's also a spacing difference, right? These have this spacing, and you can see these are slightly closer spaced. These colored blocks indicate how many molecules are in that state, right? This is e to the minus e over kt, right? This is the Boltzmann distribution, right? So you can see how many molecules at a given temperature in each state, right? And because, in this situation, because the energy level spacings are smaller in the products, remember they're both at the same temperature, there are more molecules in more states, right? There are molecules in 1, 2, all the way up here. But you can notice in this situation, there are only molecules available up until here, right? So this system is more disordered because there are more configurations to choose from, and the molecules are distributed amongst them more than they are here, right? So entropy should increase, which it does, 2 joules per mole, right? And the energy and the enthalpy difference is minus 5 kilojoules per mole, right? So that means we have minus 5 plus 300 times, minus 300 times 2, that's obviously going to be a negative value, right? So delta G here is less than 0, right? And not surprisingly, the equilibrium constant is greater than 1, right? There are more products than there are reactants. Now we can make this go extreme too. For instance, as we start to cool it down, we'll drop the temperature down to something if it lets me. Okay, it doesn't like me. Why is this not working? This was working beautifully yesterday, and now it's not. Let me restart. Okay, there we go. So if I turn it down to 100 Kelvin, while 100 Kelvin, there's far less temperature, there's far much thermal energy, And the spacings of these the reactant states are such that it doesn't even plot it, but basically all the molecules are in the ground state. Right? So you basically have all your molecules in one configuration, and then your reactants have multiple more configurations because there are more available spaces or more available configurations within the energy range, available energy. Of course, everything is getting squished because it's getting colder. But look what's happened. Because we've dropped the temperature down, we've still kept the enthalpy negative, the entropy change has changed a little bit, but because there is so little energy available for the molecules in the A state, or in the reactants to exist in them, all the energy is dominating on this side, and you get a really large equilibrium constant, right? We have a big entropy change here. And now as I change the enthalpy, right now I'm going to set the enthalpy difference to where they're about equal. So now they have the same energy, the same enthalpy. There's no enthalpy change. But because the spacings, there's more configurations in the products for the molecules to exist in at a given temperature than there is here. Right? We have 1, 2, 3, 4, 5. Well, you can't really tell the difference here with 1, 2, 3, 4, 5. There's a little bit more in the upper states here than there is here. We still have a very slight positive entropy increase. And even though there's no energy difference, the entropy ends up winning out, and this becomes very slightly product favored. So the important thing to note is that when we talk about energy differences in molecules, we're talking often tens or hundreds of kilojoules per mole. But entropy is generally a much smaller number. Right? Entropy in this case is only 1.36 joules per mole. Right? So it makes a very, very small contribution. So often when you're in the gas phase, you can do equilibrium without even worrying about entropy. Right? You can just do it with enthalpy. Right? You could write RT ln K is equal to minus delta H. Because that's ultimately what determines it to a decent amount of energy. Now we could go crazy, right? Well, for instance, let's do the opposite effect. Let's make the products more favored. Right here you have a huge, right? We have a 15 kilojoule per mole difference, and you can see the equilibrium constant is very, very product favored. But let's make it more reactant favored by making the energy spacings in the reactants very small. You can see that doesn't really make much of a difference. Right? The entropy change is only about 2.2 joules per mole, but compared to the enthalpy change, it's massive. Or it's tiny, right? It's tiny compared to this, by orders of magnitude. So entropy plays, especially at low temperature, entropy plays a very, very, very small role. Right? So when you're at low temperature, 0 Kelvin, 100 Kelvin, very cold temperatures, entropy doesn't matter at all. It makes no contribution. Very little contribution. Ultimately, what determines your equilibrium is the enthalpy, right? Energy differences between molecules, not entropy differences. That changes, though, when you get really hot. Right, so let's do the same example, but let's pump the temperature up to 1,000. Right, and now you have molecules, you have enough energy to fill all the states available. And look how small the equilibrium constant has dropped down to. Right, the entropy hasn't changed that much. Right, the entropy is still on the order of about 1 to 5 joules per mole, but we've gone from an equilibrium constant at 100 Kelvin that was 10 to the 7 to 900 Kelvin where it's 4. Right, entropy starts to kick in big time. Because remember, delta G is H minus T delta S. So when T gets really big, entropy becomes a large contributing factor. Right, so at high temperatures and high pressures, for instance, high temperatures especially, entropy becomes a really big deal. And so there are many cases of reactions, and we'll explore these, where even though you have an exothermic reaction, the product it's still reactant favored because the entropy change is so negative. Right? Entropy ends up winning out. And there are other cases. There's the opposite case, which is I'll explain to you right here at the end of the class. The more classic example are endothermic reactions where delta E is positive. So let's look at that. All right, so here's a case. Right, the equilibrium constant is 2 times 10 to the minus 1 here. And the problem is that many reactions are like this. They're endothermic. And well, if maybe we want to do a transformation from from reactants to products. But the problem is that the equilibrium is negative. But the thing is that equilibrium allows us to cheat a little bit using entropy. And let me explain what I mean by that. The important part that I want to get at is that at thermal equilibrium, where everything's random and statistical, everything is normal, at a given T, given temperature T, Kp is fixed. The ratio of products to reactants is always the same at equilibrium. So let's think about something that's endothermic, that isn't product favored, and see if we can make it product favored. Right, by exploiting the fact that the ratio at equilibrium is always the same. So here's a good example. Let's take, that's not chlorine. Let's take this molecule. All right, so that's what we call this. This is alpha, beta, delta, or alpha, beta, delta. This is delta chloropropionic acid. Or is it beta propionic and chlorobeta propionic acid? I think it's delta. Yeah. And then we're going to heat it to dissociate, and you form CO2 gas, decarboxylate it, and chloroethane. Delta H here is very large, positive. It's endothermic. Right? So the problem is that this is if this is in a sealed container, this is at equilibrium, and delta G is also greater than 0 at 298 Kelvin. Right, and that's a problem, right? Maybe we want to decarboxylate this, but we don't have the luxury of doing so, right? Because delta G is favored towards the reactants. But the fact of the matter is that the partial pressure of CO2 times the concentration of CH3, CH2Cl divided by the concentration of our acid is fixed. It's fixed. So e to the minus delta G over RT. So let's say we want to make our chloroethane by decomposing this. But the fact of the matter is if we just let this sit, we're going to almost always have just our reactants, reactant favored. All right, so how do we efficiently decarboxylate this? Well, the trick is to do this in an open container. So here's our acid. I want to write our acid in purple and our chloroethane in orange. Right, so we've got, and we'll have CO2 in black, I guess. So in our reactants, again, we have a lot of in our solution, we have lots of chloropropionic acid at equilibrium, and maybe a little bit of chloroethane. But mostly our acid. But if we leave this open, right, this reaction also involves CO2, right? The CO2 is just going to bubble out. So now let's think about what does K look like in here as this bubbles out? Well, we're going to have K is equal to the partial pressure of CO2 in our liquid times the concentration divided by our acid. I'm just going to write that RCOOH. And what happens as it bubbles out, well, the concentration of the partial pressure of CO2 drops because the CO2 leaves and escapes the atmosphere. So this quotient decreases. Right, so the numerator decreases. And so in order to reestablish K equals e to the minus delta G over RT, right? This is fixed at equilibrium. The reactant has to continue going forward, right? This also has to drop as well, which means that this is going to increase. Right, so as the CO2 leaves, K for the system at a given time gets lower, and so as the system equilibrates, well, it has to restore K back to its correct equilibrium value. And the only way to do that is to get rid of some reactants and add some products. Right, so as CO2 bubbles out, our system continuously has to decarboxylate in order to maintain equilibrium. So in fact, this reaction goes to completion. And if you wait long enough, all the acid's gone and you're left with just chloroethane because all the CO2's left. Right? The CO2 goes bye-bye, and in order to reestablish equilibrium, you have to make more CO2, which makes you make more chloroethane. Eventually, you're just going to run out of chloropropionic acid. Right? And so the idea here is that bubbling, evolving a gas, and letting it escape is very entropically favored. Right, so even though we have a reactant favored, if we sealed this container, right, if we sealed it and didn't let CO2 leave, then it's always going to be reactant favored. But the fact is that we allow the CO2 to leave, then in order to reestablish the equilibrium, it's got to make more and more CO2, which means eventually you're just going to run out of your propionic acid. Right, and so the idea is that gas evolving, the entropy of CO2 gas is very, very large because of escaping. And so ultimately you can drive this reaction to completion because you're using the entropy of a gas to your advantage to continuously drive the system out of equilibrium and forcing it to try to reestablish. Another really good example of this is with water, hydrolysis. So typically, if you have an if you have a reactant-favored or reaction that evolves H2O, or so for instance, an OH leaves a molecule and forms H2O, what we use is a Dean-Stark trap. So what we can do is something that like this. Let me see if I can draw this. This is really pressing my organic chemistry skills. So imagine you have a reaction that releases water. So let me draw a flask, a pour flask. And we heat it. And on top of it, we put a condenser. And a collection here. This is the water collection flask or a tube or something like that. So imagine you have some reaction going on inside this flask that creates water. Right? So you have, like, let's just say it's A, product favored, so it's like a little arrow and a big left arrow, B plus H2O. Right? And we boil it, we reflux it, so that you have a little bit of A's and some B's, mostly A's, a little bit of B and a little bit of H2O. And what happens is in a Dean-Stark trap, the H2O gets trapped through the reflux. The volatiles go up here and condense back down, and the Dean-Stark trap traps the water, like so. Or sorry, actually the condenser needs to be a little lower than that, right? So you condense out. Let me erase this real quick. I apologize. I haven't done this in a while. So if we condense here, if water has a higher boiling point, if the boiling point of water is greater than the boiling point of your material, of B and A, right, you have volatile organics, you condense it, the A and the B here fall back down, and the H2O gets trapped. It goes through the short condenser and gets trapped down here. And so, again, let's just write that reaction again. A, B plus H2O. Right, this is delta G greater than 0. But what we've done is every time as we reflux this and B kind of reacts to form some B and H2O, the H2O goes through the condenser and gets trapped in a water collector. So in order to reestablish, so that means that there's not as much H2O in here as equilibrium would expect. And so in order to reestablish equilibrium, you have to deplete A to form more B in water. Right? The equilibrium constant is fixed. So in order to equilibrate, you've got to make more water, which means you make more B. Same process happens. You trap it. Again, it's called a Dean-Stark trap. Right? So you trap the water leaves the reaction vessel in order to reestablish equilibrium in the reaction vessel, you have to react A's to form more B's. Right? And this process continues. So you can take this reaction and drive it to completion, even though it's not product favored, because what you're doing is you're continually driving the system out of equilibrium. Right? This kind of trapping, or bubbling, is a non-equilibrium process. Right, so the system is being continuously driven out of equilibrium, but the system also always tries to reestablish equilibrium. I can't write this low. It always tries to reestablish equilibrium. Right, so you continuously drive it out of equilibrium, trap your water, and then the system wants to reestablish equilibrium, which means it's got to make more B in water, and the process continues, right? And ultimately, with the Dean-Stark trap, A will completely go to B. Right? You just keep driving it out of equilibrium, forcing it to make more products, and eventually you just run out of A, and you have all B. Right, so organic chemists use these tricks all the time, right? Equilibrium is not a death knell for us, right? Having a bad equilibrium constant does not mean that this reaction is a no-go. Well, it means we just have to be clever, right? And as we'll learn, there are different ways to be clever. One is that you can just continuously drive your system out of equilibrium by removing one of the products or reactants, like in these two cases. And as we'll learn, we'll look at this more carefully, you can also adjust your equilibrium by changing your conditions, right? Some reactions will be more product favored at low temperature and at high temperature. Some will be really good at high pressure, some will be good at low pressure. Some will be good at low concentration, some will be good at high concentration. So the remainder of our equilibrium time will be to look at those situations, right? How can we... Right, that's the ultimate goal that we have as chemists, is we want to do something interesting, and maybe thermodynamics doesn't let us do something interesting, right? Thermal equilibrium doesn't let us do something interesting, and so what we can do is we can cheat it. We can either cheat it this way by driving the system out of equilibrium, or we can figure out what conditions we need in order to make it product favored again, right? And so one of the examples we'll look at is the Haber-Bosch process, which is the classic way to make ammonia industrially. That's an extremely important reaction because you don't have fertilizer without ammonia, right? So all of modern agriculture is built on the Haber-Bosch process. And as we'll learn, the Haber-Bosch process, if you don't know, is the formation. We'll talk about this on Tuesday. It's the reaction of H2 plus N2. And this is actually at room temperature reactant favored to form NH3. Now that's not balanced, so this is 3, yeah, 2. Yeah, there we go, 2 NH3. Right, Haber-Bosch process, right? So at room temperature, RT, this is delta G greater than 0 and slow. But it turns out that if you can play around with the conditions a little bit, you can not only make it fast, but you can also make it product favored, right? And this reaction changed everything about agriculture. There wouldn't be agriculture in the third world without this, because there's no way to make fertilizer efficiently and cheaply without using the Haber-Bosch process. Ironically, Fritz Haber, despite the fact that he basically revolutionized modern agriculture and saved millions of people, he also developed the chemical weapons that were used in World War I and the Holocaust. So he has kind of a crazy history. And he eventually killed himself after killing his wife and his children. So kind of a crazy man. So we have a lot of things to blame him for, but also things to thank him for. It's a very interesting story. But we'll look at this in careful. We'll look at the mechanism of this when we do kinetics. We'll talk about it on Tuesday, but I'll also talk about the equilibrium. Right? How do we take this reaction and make it favorable? All right, so that'll be our first project, if you will, our first example of equilibrium, and we'll work on that on Tuesday. We'll also talk on Tuesday about the kind of traditional approach to equilibrium, right? This idea of, we'll introduce something called the extent of reaction, a way to track G as we change the products and the reactants, right? We drive the system out of equilibrium. How does the system reestablish equilibrium? So we'll talk about the math of that, which will allow us to get some tips and tricks and some tools that allow us to use equilibrium for our own uses. And we'll use the Haber-Bosch process as our example. Okay, that's all I got for you today. Thanks, everybody. If you have any questions, I'll take them. But otherwise, have a lovely weekend. I'll see some of you tomorrow. And I'll see you Tuesday.
Every Thursday it's in Max, you know?
Max,
1 through 6.
I'm gonna
Be there.
No, I
I'll be
checked.
there.
I have it. I will credits. But I can just change my elective.
I sent it.
I can change that.
Oh, it's great. You're much better than me.
So it'll be all good. Is she pretty? Yeah.
I
I wasn't gonna draw one, but then I'm like, no, I should draw one, so I drew it in like 20 seconds. And I'm like, we got colors, guys. It's so colorful.
I'm proud of my flash. It looks like a real glass.
Oh, he does? Oh.
Yeah, much better mine. Mine looks like.
My dad, I was looking at yours, I was like, okay, what's it? It looks a little like a shovel. Like
Yeah,
a
that's
little
right.
beach shovel.
Yeah, that's right. That's like a beach
The
shovel.
grad seminar is virtual this week, right?
That's correct.
All right.
Can we still show up?
Yeah, of course. Yeah, I'll still be there.
See you.
Take care.
See you like in an hour.
See you
Have a
in
good
an
one.
hour. I'll be there.
You want to walk to FSSA together?
Yeah, I just got